Hi everyone, I am Yamini, Department of Computer Science and Engineering, SNS College of Technology. Welcome to this video on asymptotic notation and their properties, part of Unit 5 in data structures. In this session, we are going to understand why asymptotic analysis is important, the the different types of notations and the properties that helps us evaluate algorithm performance. Let's get started.
The topics are going to cover in this video: need for asymptotic notations. When we analyze an algorithm means its except runtime is difficult because it depends on a system, processor, compiler, and many other factors. So instead of looking at actual time, we focus on how the algorithm grows when input size increases. This is where asymptotic notation helps. It gives us a universal, machine independent way to compare the efficiency of algorithm. Next topic: types and data stages and then properties. Next one, asymptotic notation definition. In asymptotic notations or mathematical tool need to describe the efficiency of an algorithm in terms of time and space complexity when the input size n becomes very large. Next one, that is an example for asymptotic notation. Consider a two algorithm. Algorithm A takes 100 n pulse 5 steps, while algorithm B takes 100 n squared pulse 5 steps. For small input like n equal to 2, both run quickly. But as n grows large, algorithm A grows linearly. Y algorithm grows B is a quadratically. So A is more efficient for large input. This example shows why analyzer growth matter more than actual runtime. Next one, asymptotic notation, and it is a property. That is, the asymptotic notations are mathematical tool used to represent a time and space complexity as input size become very large. This helps us focus on a demonstrate terms in a function, ignoring constants and lower order terms. This gives us a clearer idea of algorithm performance in real world scaling situation. Next one, Big O notation. In Big O notations represents the upper bound of the algorithm. It tells us the worst case scenario, the maximum time an algorithm might take for larger input. Finally, we say f of n is big O of g of n. If f of n is always less than or equal to some constant time g of n, beyond a certain value of n, big O is the most commonly used notations in complexity analysis. Next one, omega notation. In omega notation, this gives the lower bound of an algorithm, means the best case performance. Omega tells us the minimum time an algorithm is guaranteed to take no matter what. Formally f of n is omega of g of n if f of n is always greater than or equal to constant time g of n for large value of n. Next one is theta notation. In theta notation, that is, there is a tight bounded of an algorithm. It combine both upper and lower bound. In an algorithm is both big O of g of n and omega of g of n, then it is theta of g of n. Theta represents exact or average case time complexity for most algorithms. Next one, that is an properties of asymptotic notation. Asymptotic notation follows several useful mathematical properties. Reflexive, every function is O if itself. Transitive, if f is big O of g and g is big O of h, then f is big O of h. In symmetric for theta, if f is theta of g, then g is theta of f. Inverse relation, if f of big O of g, then g is omega of f. Therefore, properties help simply complexity expressions and compare algorithm easily. Next one, in this stage, that is, in this stage, we observe the running time measurement needs improvement. We realize that executing time varies across system, but user wants speed and efficiency. This understand motivate the need for universal measure system asymptotic notation. Next one, in this stage we frame a core problem. How do we express algorithm growth as input size increases? Here we introduce big O, big omega and big theta notation to capture a worst, best and tightly bounded respectively. In next stage, in this stage, we explore various growth functions like a constant time, algorithmic time, linear time and quadratic time. Visualizing these curves helps us understanding how different algorithms scale as input size grows. Next one, in this stage, prototype stage, that is, we apply these notations to real algorithm. Linear search become big O of n. In binary search become big O of log n. In bubble sort become big O of n squared. This gives a practically understand for performance difference. Next one is testing. In testing stage, we evaluate how asymptotic notation helps in choose the best algorithm. Comparing big O value helps us pick scalable solution. We validate our theoretical results with experimental output makes decision more reliable. In mind map, here we quickly mind map summarizing everything. The need for notation, types of asymptotic notation, their meaning and properties. This gives a clear overview of entire concepts. Thank you.